I'd like to spend some time going through uncertainty calculations. To start with, there is a difference between the word error and the word uncertainty. The error is the difference between a measured value and the accepted value. The uncertainty is an indication of the reliability of a measurement, and this is often preceded by the symbol plus or minus. Today, we're going to look at this experiment. This is a fairly common experiment at both GCSE and the sixth form. There's a spirit burner and a copper can, often called a calorimeter, and inside that is water and a thermometer. And this experiment is used to measure the enthalpy of combustion of the fuel in the spirit burner. Here are the results from a typical experiment. And these are all of the values that would be measured by the student. So the initial mass of ethanol and the spirit burner. So notice this is given to 2 decimal places because that is the maximum accuracy of the balance. The final mass of ethanol in the spirit burner. The mass of water in the calorimeter. And because this is often measured using a measuring cylinder, this is given in cubic centimetres. The initial temperature of the water and the final temperature of the water. Notice that both of those values are given to 1 decimal place. These values that I've given with the plus or minuses are what we call absolute uncertainties. They're absolute because they all have the appropriate units that correspond to the original measurement. So they're not percentages. These are absolute uncertainties. As a general rule, if you check the equipment that you're using, very often the uncertainty is written on there. So for example, I have here a measuring cylinder, and sure enough, written on there, you might just be able to see I've put a post-it behind it, is the uncertainty. In this case, plus or minus 1 milliliter or 1 cubic centimetre. So always check the equipment that you're using. So it might be on the side of a thermometer or on the balance that you use to weigh things. If the value is not given, the general rule is that digital equipment is plus or minus the smallest division. So in this example, the mass was measured using a digital balance, and the smallest division was 0.0 grams. And this is the uncertainty that I have used for those values. If the value is not given on the equipment and it is a piece of analog equipment, so not electrical equipment, analog, the general rule is plus or minus a half the smallest division. So in this situation, the temperature measured with the thermometer, the smallest division on the thermometer is 1 degree Celsius. That means the uncertainty is plus or minus 0.5 degrees Celsius. Notice that for the measuring cylinder that we use to measure the water, the uncertainty is plus or minus 1 cubic centimetre. This is because this value was written on the side of the glassware. So these are the general rules for calculating absolute uncertainties. Here's a typical calculation for this type of experiment. The mass of ethanol burnt is calculated by taking the initial mass and minusing the final mass. So obviously, as the ethanol burns, it loses mass. And so we get this number here. Now, the rule with calculations is that when you are adding or subtracting, you keep the number of decimal places. So the number of decimal places in the final answer is limited by the smallest number of decimal places in the preceding calculation. So in this situation, both of my numbers are to 2 decimal places. That means that my final answer will be to 2 decimal places. Similarly, for the temperature change, both of my values are to 1 decimal place, and that means that the final answer will also be to 1 decimal place. For the moles of ethanol burnt, we just take the mass and divide it by mR, the relative formula mass. In this situation, when we are multiplying or dividing, the rule is to be limited by the smallest number of significant figures. In this case, mR is an exact value that we've taken from the periodic table, so we do not look at that. We have 3 significant figures on the top here, on the numerator, and that means that our final answer should be to 3 significant figures. In order to come up with a final answer for delta H, the enthalpy change for the combustion of ethanol, we use this equation. The minus sign is included because, of course, this is an exothermic reaction. The value of C is 4.18. This is the specific heat capacity of water, and that just comes from the data booklet. This is the mass of water in the calorimeter, the temperature change, and the number of moles of ethanol burnt. Because we are multiplying and dividing in this situation, we are limited by the number of significant figures. Looking at what I have here, all of these numbers are to 3 significant figures, and that means that our final answer should be to 3 significant figures. I've divided it by 1000 to convert it into kilojoules per mole, because that is the usual form for this type of calculation. For this same experiment, we can work out the absolute uncertainty in our final answer. And we do this by working out, first of all, the percentage uncertainty in each of the components that we measured for our calculation. So going back to the previous page, we can see that in the calculation of the final answer, we have had to use 5 different numbers. We have had to use 2 masses, the initial and final mass of the ethanol. Both of those were measured separately. 2 temperatures, the initial and final temperature. Again, those have been measured separately. And also the mass of the water in the calorimeter. So in order to create this final answer here, minus 406 kilojoules per mole, we have had to make 5 different measurements. And those are the 5 different measurements here, and each of those 5 has an absolute uncertainty value associated with it. In order to calculate the percentage uncertainty, we simply take the absolute uncertainty for each measurement and divide it by the measured value, multiplying by 100% to convert it into a percentage. The same rules apply here for multiplying and dividing and significant figures. You do have to be a little bit careful. So for example, in this top one here, we're limited by 1 significant figure. So that means that we have 1 significant figure in our answer. Again, 1 significant figure yields 1 significant figure. 1 significant figure yields 1 significant figure. 1 significant figure again, and 1 significant figure again. So just keeping it simple. In order to calculate the overall percentage uncertainty, we simply add the percentages together. So the process of converting those absolute uncertainties into percentages means that they've been appropriately scaled and they can be added to each other directly. So again, when we're adding or subtracting, we are limited by the smallest number of decimal places. In this situation, we're limited here, so there are 0 decimal places, and that means that there are 0 decimal places in our answer here. In order to work out the absolute uncertainty in the final answer, we take our calculated value of delta H, which was minus 406 kilojoules per mole. That's just from the previous calculation. We take that as an absolute value. And we take the percentage uncertainty divided by 100. And when we do that, we end up with plus or minus 10 kilojoules per mole. Again, because this involves multiplying and dividing, we are limited by the number of significant figures. So this 3 is to 1 significant figure, and that means that our final answer is to 1 significant figure. So our overall answer for this experiment is minus 406 kilojoules per mole plus or minus 10 kilojoules per mole. And that plus or minus 10 is, of course, the uncertainty in our final answer. We could go on to look at the literature to find out what the literature value is for the enthalpy of combustion of ethanol. And the difference between that universally accepted correct answer and our measured answer here would be called the error. In reality, our value here is much, much less negative than the literature value. And there are 3 reasons for that. First of all, a lot of the heat from our experiment will have been lost to the surroundings. Some of the water in the calorimeter will have evaporated, so we can't assume that the mass of water is constant. It will also affect the temperature change. And finally, there will be some element of incomplete combustion in the ethanol during this experiment.